Yes. Sure. Yeah, that's fine.
I think we'll go ahead and get started. I want to welcome all of you to the the afternoon's event here, a conversation with Toney Hey on how does data empower scholarship. We're really glad to have Toney and his wife back on campus. It's a real privilege to host them here. They were here, I think, about 3 years ago, and we promised them good weather, and sure enough, we made good on that promise. We want to welcome the folks that are joining us remotely from the University of Tulsa, and I think there may be some from Oklahoma State as well. My name is Kelvin Drogemeyer. I'm a faculty member in the School of Meteorology and also the Vice President for Research here at OU, and I have the privilege of providing a few opening comments to sort of set the stage for the good discussion this afternoon. So I'll just go ahead and jump right into that. First with an observation. I'm a meteorologist. We like to observe the world, and we do some interesting things as human beings. We do something really amazing. Now, no, I'm not speaking about or for Donald Trump here. Something really cool. It's going to be really wonderful. It's going to be really amazing. We do something amazing, and then sometimes we're overwhelmed by what happens, and some expected issues emerge. Can you all think of examples of that in your own sort of daily activity where you've seen that happen? We sort of figure out then how to manage. Then we learn to take advantage of something. And then after we learn to take advantage, we make improvements and new ideas emerge. And just think about the splitting of the atom, right? So fission was discovered back in the late 20s, early 30s. We were kind of overwhelmed and unexpected issues emerged, like using atomic fission for destructive purposes. We figured out how to manage this through controls and treaties and things like that, positive control systems for managing nuclear weapons. Then we learned how to take advantage of it in terms of nuclear power. And of course, we made improvements and new things arose, like the ability of using nuclear power for medicine, nuclear medicine. So it's very interesting when you look at things like this that happen. Something sort of happens that surprises us, but we adapt to it. Another thing, of course, is information technology. That picture at the top where it says "you are here," that's the internet. A lot of unexpected things emerge, like Facebook and so on, which gives rise to all manner of communication, good and bad. People sort of telegraphing where they're going to plot bombings or make, cause great death and destruction and so on. We do figure out how to manage that sort of thing. I think we're still looking at that right now. We learn how to take advantage of it, things like eBay and, of course, all the online commerce that happens now and making improvements. Gee, look at all the online learning capabilities that have been enabled through information technology. So it goes. Today we're talking about something that I think is equally as powerful and transformative, and that's the notion of open access to information and data. It's a very complicated thing. As you sit down and think about what we mean by this, really there's a whole huge spectrum of data, all the way from, on the far left, there are zillions of tiny data, little tweets and things like that describe what people are thinking at the moment. It might be related to earthquakes, it might be a natural disaster, it might be a murder that's happening somewhere. They're highly perishable, you can't reproduce them, they happen in real time. All the way over to the right, which is the world I kind of live in, which is these very, very large, massive data sets that are sort of single in their existence. They don't consist of lots of pieces, although they're made up of pieces, but you have to deal with the whole altogether. And so there's this massive spectrum of information, and it comes at you at different speeds, it comes at you in different structures, so-called velocity of data, the variety of data, so on. You can describe in a lot of ways. And there are lots and lots of questions out there when you think about making data available openly. What is data? What are data? How do we even define it? Who owns it? Who decides who owns it? Who decides what should be kept? We talked about this at lunch. You can think about the raw data, the metadata, all kinds of data descriptors. Do you keep all the data you produce or only some of it? Quality controlled, so on. How and where should be kept and who decides? And how is quality assured and who determines what the quality assurance is? Who provides access and who pays? This is a world that we in universities live in. Dean Luce here at the library and myself and the provost were talking about this even the other day. Who provides access and who pays? And who pays for the persistent curation of this information? Who's given how is access provided, right? That's very important. Who is given access and when, and who decides who gets it? And maybe for how long. If you deny access, who decides that? Who provides the technical assistance? You put a lot of data out there, you're a scientist, you're doing all your stuff, and you have some groundbreaking research, you put the data out there, and now all of a sudden your email box is filled with people saying, I can't decode the data, how did you do this, how did you do that? Tremendous opportunity for collaboration, but also potentially a tremendous burden. How do you mediate between those two things? Credit. Huge, right? We've done tenure based on publication, that kind of thing primarily, but now people producing data sets, that's a very valuable contribution to scholarship and scholarly enterprise. So how do we assign credit? And then of course, compliance issues, all kinds of compliance. It's very interesting that we're roughly at the 3rd anniversary of the federal government's, in the US, proclamation that any agency that provides more than $100 million of research funding shall have a policy for open access to data. And that happened 3 years ago. There are now 16 federal agencies that span about 98% of all the federal research that's funded in this country actually have policies. So what's really nice is we're seeing the ability for people to get out there and not only put their data online, but to access data from other disciplines and so on. So the world is changing, and it's going to be a gradual change. As I talked with Tony about at lunch, it's not something that happens overnight. We're going to have to learn how to use data and how to not misuse data. It's very, very interesting points. When you think about the notion of sharing, Kyla over there has a young child, right? What's the first thing that child says? No, it's mine, right? Well, we learn that sort of at an early age. It's kind of innate behavior, and faculty sometimes are no different. No, this is mine. It's my grant that produced it, and it's mine to have. In the academy, we reward people primarily for their own scholarly activities. We tend to encourage collaboration, but at the end of the day, what we evaluate is mostly what did you do? What did you do individually? So why would we share? Well, it's required. Okay, well that's one good reason, to enhance our own scholarship, a little bit less selfish, to enhance our discipline, a little bit less selfish, to enhance our academic program, our institution, bring benefits to the nation, and frankly to improve the world. And I think that frankly most faculty are very kind of altruistic in their thinking. They really want to not only advance the state of knowledge in their discipline, they want to help other people be successful as well. So the notion of sharing is interesting when you think about it. So the end game for research, me as a VPR, as a scientist, what do I think is going to happen? I think that open access will enable new and better ways of doing old things plus lots of new things. So I kind of would put it like this. Reproducibility is a very important thing. Being able to take somebody's results and reproduce them as you're doing other things, as you're building upon their body of scholarship. That's a very important, kind of a difficult thing. It's in the news, it's in Congress. This is a very, very important issue, complicated though it may be. Reproducibility is something that really open access, I think, will greatly contribute to. Extensibility, expanding and building upon previous scholarship. This is what science has really always been about, but open access is going to, I think, transform the notion of how we actually do that. Collaborability, it's not a word, I made it up, but we're talking about really now working across disciplines. People that are interested in human behavior and maybe disease and other things get climate science data sets and they use them for interesting work in their own scholarly field. Though they're not an expert, they now have access to that. And then finally, creatability, another word I made up, but this is the blank sheet of paper, the frontier research that I think we don't even know and can't really predict what open access will mean. Some of it we can, but some of it we can't. So I think it's extremely exciting, and I think we're really very, very fortunate today to have one of the foremost leaders of the world who thinks about open access from a technology point of view, from a scholarly point of view, from a science point of view, from a human behavioral point of view, and ultimately from the point of view of making sure that we then apply science to the betterment of mankind. And that is Toney Hey and his wife Jessie. So with that I will end, and I will turn it over to Dr. Steve McKeever, who is our Oklahoma Secretary of Science and Technology. He's also the former Vice President for Research at Oklahoma State University, and he has an endowed chair, the most endowed chair. I don't think most is an acronym, actually, it turns out. The most endowed chair, the baddest endowed chair, the best endowed chair is Steve McKeever in the Department of Physics at OSU. So let's please give Steve a warm welcome.
Well, thank you very much, Kelvin, and thank you all for being here, and hello to Tulsa and my friends and colleagues at OSU. I always learn something new whenever I'm around Kelvin, and today I learned two new words, collaborability and what was the other one? Creatability. I don't know if they exist, but I love them. There's a serious point to be made there, because I love them. Because those two things, especially the first, in order to lead into the second, are exactly what Oklahoma as a state needs to be doing. I have the honor of chairing the Governor's Advisory Council on Science and Technology, of which Kelvin and others are members. And during the course of our discussions about what to do about science and technology throughout the state and how to grow that enterprise for the economic benefit of all of us, throughout the course of those discussions, somebody pointed out, and I can't recall who on the council it was now, that if you added together OSU, OU, and TU, you'd have one university the size of Texas A&M. Now that's very revealing. It was revealing to me because it's the Texas A&Ms of this nation, of this world, that we are competing against when it comes to establishing ourselves as a credible area for doing creativity within the realm of science and technology. With size comes resources. With size comes capabilities that you simply don't have when you are a smaller institution, a smaller unit. But if we think of Oklahoma not as an area that consists of a number of major universities active in research, but rather as a state active in research, then you start to think of Oklahoma somewhat differently than perhaps the way we have done in the past. And so we coined the phrase, One Oklahoma, sort of one word, One Oklahoma. And in 2012, we wrote a strategic plan for the development of the science and technology enterprise within the state, and we called it the One Oklahoma Plan. We were gratified to see that that notion really had traction within especially the three major research institutions. It also had traction, though, in Lincoln Boulevard at the state capitol among our legislators. Finally, they and we were saying, we are thinking about working together and not competing. We can compete on the football field, the baseball field, the basketball field, but when it comes to this kind of activity, we have to collaborate. So the notion of One Oklahoma really did appeal to such a lot of people. There's a wonderful example of that immediately sprung up around that time, and that was an activity led by OU's Henry Neiman and the establishment of a statewide high-performance computing capability. And indeed, they called it, I think initially part of its plan was the One Oklahoma high-performance network, something like that. But Kelvin, you were mentioning over lunch, the latest version is called One Okie, is it? Yeah, One Okie. I've forgotten what the acronym stands for, but the notion again is that by putting together those major computing resources, we, Oklahoma, can compete in that area with just about anybody within the nation. Certainly combined, though the computing power there must be up in the top 25 or top 20 or perhaps even higher within the nation. That is a wonderful example of what can be done. Another wonderful example is perhaps a more recent one in the area of unmanned aerial systems. For those of you who are unfamiliar with that phrase, perhaps you'll know what I mean when I say the word drones, the development of drones. Now, the collaboration that has grown out of that activity actually came out of a failed effort to write a proposal. Well, actually, we didn't fail in the effort of writing the proposal. We failed in the effort of getting the proposal funded. By the way, I do have to shout out Marilyn Cahonan for leading. She was the program manager on that effort. What that effort succeeded in doing was to bring together people of like minds in Oklahoma and say that we need to present ourselves as a single state doing a single activity in a coordinated fashion. And we even brought in the highest levels of government through the governor and the governor's office and major state legislators and leaders who backed that effort. And we presented ourselves as a team like no other state. And indeed, that comment was made by the FAA and by our competitors. Nevertheless, we didn't quite make the cut, for which we now say, thank goodness we didn't make the cut, because there's a lot of baggage that actually came with that effort. But the positive benefit is now being seen within the state. In particular, the expertise, the world-renowned, world-leading expertise in meteorology at OU is being combined with the similarly world-leading expertise in drone development at OSU, and hopefully we're going to build into this program the world-leading expertise in cybersecurity from TU to develop the capability of exploring the lower atmosphere using drones to provide the capability of weather prediction like the world of meteorology has never seen before. And indeed, just recently, that combined team announced a $6 million award from NSF. So those are two great examples of this notion of One Oklahoma, what we can do together. Interestingly, this whole concept of working together brings us very naturally, I think, to today's topic, which is open access to data. Now, the discussion this afternoon, excuse me, the discussion this afternoon will expand far beyond the borders of Oklahoma. But I think that within our borders, within the borders of Oklahoma, the notion of data sharing and experience sharing can benefit and enhance what we're trying to do here within our state, to think of our major universities as, in fact, just different campuses of the same effort. The notion of data sharing will become extremely important. Unfortunately, we have a collection of experts today to talk about that on a wider scale. But as we do go forward within Oklahoma, as we do talk about our research agenda within the world of science and technology, we need to bear in mind what it is we can do to benefit ourselves as we share our, not just our resources, but also our data and our information. I love the cartoon that Calvin showed there of the children pulling over the teddy bear, over the toy. And indeed, let's face it, that's the way we have tried to move forward in past decades and past years, apart from a couple of wonderful illustrations where that didn't happen. That nevertheless has been the rule rather than the exception. And how awful it would be if that's the way we continue to move forward in the future. Another aspect of this whole concept of working together to develop the science and technology capability within the state surrounds the notion of who will be doing that science and technology in the future. I mean, the individuals. Who will they be? More particularly, where will they come from? As we know in our universities, we rely very heavily and wonderfully on the out-of-state, indeed out-of-nation experts who come to enrich the experience that we have here in our universities and in our scholarly enterprises. And long may that continue. But also we need to think about growing our own, which brings us to the concept of STEM education and what it is that we need to do together within this area to improve the future of science and technology within our state. And there, perhaps the most important word that we need to think about is collaborate, or collaborability. When we think about all of the different sectors within the state that impact STEM education, we can think of the K through 12 system, we can think of the career tech system, we can think of the higher education system. And regrettably, those are three silos that rarely talk to each other. That has to change. And who are the beneficiaries of this education system? Industry, both national industry and indeed international industry, but also our state industry. Our state industry is built upon oil and gas and energy. It's built upon aerospace, agriculture, security and defense, transportation, all of which are science and technology businesses. For sure, they have accountants and graphic artists and historians and English majors, etc., working for those industries. But the core industry is not a graphic artist or a historian. It is a science and a technology industry at its core. So if we are to build those industries, and if we are to build the scholarly enterprise that we require within our One Oklahoma notion, we need also to have a One Oklahoma notion about STEM education, which means that we have to collaborate and work more effectively. Perhaps the glue that will hold all those entities together is not our legislators, it's not our higher education authorities or our K through 12. Perhaps the glue will come from our communities, our mums and dads, our local industry, our local leaders, who will say that we have to come together to talk about this issue more carefully than we have done so in the past. We need two core concepts to be really enforced. One is rigor, and the other is relevance. And if we can achieve that, we will have achieved One Oklahoma for our STEM education. Well, let me just wind up before I introduce the person who will introduce our guest by just saying the following. Regarding open access of data, the whole notion of open access of data would simply not have been possible without the information technology revolution that we have seen in the last years and decades. We couldn't possibly be talking about this if we didn't have the computational power that we currently have. A colleague of mine in the UK that I used to work with and still have contact with is currently writing a book on both the benefits and the negatives that go with the development of science and technology, and one of his chapters is devoted to information technology and the digital age. And he has a theory that he expands upon in that book, in which he says that the ease with which you can put down data in a medium is inversely proportional, not directly inversely proportional, but nevertheless it has an inverse relationship to the lifetime of accessibility of that data. And the examples he uses are that if you think about the words that were carved in stone by Stone Age man, or by the ancient Egyptians, we still have them. Not all of them, of course, but we still have them. We can see them in our museums. But think about the email you wrote this morning. Will that still be around 2,000 years from now? I doubt it. His point is that as we commit more and more data to the digital medium, how easy will it be for us to access it in the future? And secondly, how easy will it be to extract from it the information? And for that point, he makes the point that some of the material that he himself has written on his office computer was done in software that you can't buy anymore, and that modern software can't read anymore. So as we think about access, it's all very well if we have access to this data, but if we can't read it, what benefit is it? So with those questions, and that's what they are, questions, I will hand it over to the experts who are here in the room, who are far more expert than I on dealing with these issues, who have thought about these issues a lot more extensively, about all of the benefits that Kelvin pointed out, and perhaps some of the negatives that go with it. So with that, I would like to introduce Richard Luce, who is the Dean of University Libraries and the Peggy Helmerich Chair and Associate Vice President of Research at OU, who will have the honor to introduce our guest of honor here this afternoon. Richard.
Thank you. It's my pleasure to be able to introduce and welcome to OU Toney Hey, who began his career as a theoretical physicist with a doctorate in particle physics from the University of Oxford. After a career in physics that included research positions at Caltech and CERN and a professorship at the University of Southampton, he became interested in parallel computing and computer science. In the 1980s, he was interested in parallel computing and in computer science. He was one of the pioneers of distributed memory message passing computing and co-wrote the first draft of the successful MPI message passing standard. In 1987, Toney Hey was asked by Caltech Nobel physicist Richard Feynman to write up his lectures on computation. This covered such unconventional topics as thermodynamics of computing, as well as an outline for the quantum computer. Feynman's introduction to the workings of a computer in terms of the actions of dumb file clerk was the inspiration for Toney Hey's attempt to write a popular book about computer science. After being both the department head and dean of engineering at Southampton, he went to lead the UK's groundbreaking eScience initiative in 2001. Recognizing the importance of big data for science, he wrote one of the first papers on the data deluge in 2003. Hey joined Microsoft in 2005 as vice president and was responsible for Microsoft's global university research engagements. He worked with Jim Gray and his multidisciplinary eScience research groups and edited a tribute to Jim called The Fourth Paradigm, Data-Intensive Scientific Discovery. Toney left Microsoft in 2014. He spent some time as a senior data science fellow at the University of Washington at the eScience Institute, and now he is chief data scientist at the Science Technology Facilities Council in the UK. He's a fellow of the AAAS and of the UK's Royal Academy of Engineering. In 2005, he was awarded a CBE, a Most Excellent Order of the British Empire, by Prince Charles for his services to science. Please help me welcome Sir Toney Hey to the podium.
Hi, well, it's a great honor to be here. So let's see if I can get my talk up, which I should be able to, since it's a Microsoft computer. Okay, so let's go. Okay, There are many things I could talk about on the open access agenda, open science, and open data. And so I've just put a few slides together, which I'll generally talk around, but they're part of a larger context. I should explain my introduction to this came about when I was Dean of Engineering at Southampton, that the university library used to send me a piece of paper every year saying, which journals do I want to cancel? That was all I got. And it became clear to me that although I was Dean of Engineering and had to write a report on the research of the faculty during the year, the university library could no longer afford to subscribe to all the journals that my 200 faculty and my 600 postdocs and graduate students published in. And so at that point, it became clear to me that we needed to keep a digital copy of everything they produced. So that's the research papers, but there's also grey literature and reports and other things too. And that should be in a repository for the engineering faculty. And that eventually, I was not there to see the end of it because I left to do the eScience program, but that eventually became the University of Southampton's institutional research repository. And my department, the Electronics and Computer Science department, was the first department to have a mandate for all its academic staff that they were obliged for their annual promotion review to have all their papers in the research repository. And that's now a university-wide mandate. And my wife actually was a digital librarian who was responsible with some others for implementing the university's research repository across all the faculties, because they're all very different. Arts and humanities are very different from maths and so on, and she can tell you in great detail just how different they are. So then the other anecdote I should just say is that I don't quite know how it happened, but I used to get invited to library conferences, and my message was change or die, all right? But for some reason they kept inviting me back, so I elaborated on it. I think if you tell it with a few jokes, it sort of goes down better. But the reason was that to a first approximation, my students in engineering and in the science faculty never went into the library for research purposes. They went there to use the email, do Wi-Fi, a cup of coffee, to warm place to work, chat to their friends. And that, as you all know, you can do in Starbucks. Right? And my son at Berkeley wrote most of his thesis sitting in Starbucks, rather than a library. So I care about libraries, and I really believe that libraries need to reinvent themselves to be the research focus of the university, as they used to be. And open access to publications and to data, as I'll try and explain, I think gives them the opportunity to become central to the research agenda. How can you claim to be a really important research department, my department for example, if nobody's reading and citing your papers? And actually you can show, if you have your papers available so people can download not just the abstract but the full text, that actually your citation impact goes up. And that's really what you want for the research reputation for the library. So I regard an institutional research repository as a key tool for reputation management for the university. For Oklahoma University, OSU, Tulsa, I believe that's the case. Enough. So let me just carry on then. So let me just say a couple of slides about the vision. And this is what Jim Gray and I decided that, as we'll hear tomorrow with Galileo, essentially started systematic experimental science, and then with Newton, who put together the works of Copernicus, Kepler, Galileo, and so on, all together to form theoretical science, the laws of nature, and you can analyze the two paradigms were experimental science and theoretical, and you can analyze machines, equations using mathematics and so on. But in the 1950s, we invented computers, and now we can do things like, for example, at the National Weather Center, you can predict the weather, you can actually do climate change calculations that you can't actually solve analytically because they're too complex and there's much to much complexity, but you can simulate, you can do experiments, you can do black hole creation, you can do galaxy formation, which you cannot do any other way. And for doing that, you need a whole set of skills to know about algorithms, numerical methods, parallel computers, programming, and all that sort of stuff. And you train those people. And some people are extremely talented at writing scientific software. And those people need to be cherished as much as the people who lead the grant and is the PI on the grant. And so one needs to think about career paths for scientific software developers. But what Jim and I were agreed upon is that increasingly we come across now scientists being overwhelmed by the amount of data. It's no longer possible for you to take it away on a simple USB stick, your data. It's too big. Even if you're a social scientist, you may not be able to get all the data on your particular workstation. You have to access different data sets in different places. You need to combine it together. So it's not just the sciences and engineering. Almost every field is being overwhelmed. In our field, you have the instruments, and so you have these radar facilities for predicting tornadoes, for example, in Oklahoma. You have huge simulations of all sorts of complicated systems and processes. Sensor networks generate huge amounts of data and so on. And how do you look after that? How do you manage it? And all those sort of things are the sort of tools and skills that we were trying to develop in what would be in the US recognized as our cyber infrastructure initiative. We called it eScience. And this is the vision of Jim Gray. And this is a slide from Bill Gates, bizarrely. And it's a vision of where you might want to go. You get a paper, and actually, if you want to get the data, you just click on it and you go to the data set. And you don't have to take measurements or write to people and things. You can get the data. The documents can be dynamic, it can be updated. You can go to the figure, you can find out what the parameters were, you can change the parameters, you can change the visualization, you can run it with different data and so on. So you have much more interactivity. And that vision for reproducible research on the paper is, I think, a very valid one. Another vision we had in the early days of eScience was this project here, where you had scientists who create data, which some of them are research papers, some of them are conference papers, some of them reports, and they're held in various things, the publishers, the institution, or just your local web server, and then it becomes part of a digital library, which can be used for teaching undergraduate students or training graduate students, and actually used in experiments again. And this was the sort of vision that we had. Where things have been galvanized is what was referred to earlier, is the White House memorandum in February 2013. This is not the open data one. This is the one for increased public access. It was followed up by the open data one. But it required agencies to develop a plan for allowing the public, whose taxes have paid for the research, to actually see the research. It also made an attempt at defining what it meant by research results. So it's not only the published paper, but it's also the data on which the results in that paper were dependent on. And this is where it defined digital data. Digital recorded factual material commonly accepted in the scientific community as necessary to validate research findings. Okay, so there's a lot of other stuff, but that's the basic idea. So let me just take a few quick examples, and then we'll come back to the influence of what as a university we should be doing, what Oklahoma should be doing, and what globally is happening. So this is the US position, but it's mirrored all around the world, and certainly in the UK we have and the European Union, they have similar initiatives here. So let me just look at some of the data services that are offered, just to give some scale of this. So in Europe, we have a thing called the European Bioinformatics Institute, EMBI. And what it does, it provides lots of data sets. So you can go there and you can get the latest genetic data set and so on. And just to give you an idea of the amount of effort that these people do, let me take one example. It's a joint example between the NIH, the UK, and Japan, and it's called UniProt. It used to be called SwissProt. And just to give a scale, it has 100 FTEs, full-time people working on it, and around 40 full-time curators on this one database. Right. And the idea is that they have, that if you just archive your data that you've taken, it can have thousands and tens of thousands of users. This one actually has very detailed annotations, which are comments on the data, what reliability is, what's been done on it by these professional curators. These have millions of users. And you might say that that sounds, 100 people being employed on a project on a yearly basis is a lot of money. Well, the literature that they curate is around 10,000 papers a year, which is around $1 billion of research funding. So in that context, this is a very small amount, $12 million, just to do the curation of that, when you have $1 billion of research funding. But that's the scale. It's a very big enterprise. And there is a problem in this particular field in bioinformatics in reproducibility, and this is why I wanted to do that. This is a review in May 2012, looked at about 2,000 articles in PubMed, the abstracts that NIH have in the National Library of Medicine. They found 20% of these were retracted because of errors that the authors had made, but an alarming 67% were retracted because of scientific misconduct, not necessarily fraud. Some may have been duplicate or plagiarism, and that's disturbing. But I think more disturbing to me was another study done by Bayer and Amgen, which concluded between, remarkable, 60 and 70% of biomedical studies may be non-reproducible. And one particular thing I should mention, that Amgen's scientists looked at 53 specific papers on a particular form of cancer that were published in Science and Nature, two of our most respected journals, and they were only able to reproduce 7 out of that 53. That's not to say the others were wrong or fraudulent. They may have been, but it may be that there wasn't enough data to enable you to do it. They hadn't told you what the methods, how they prepared it. So it's other people say, well, actually, the Amgen scientists weren't very good. All right, that's another possibility. So there are many reasons for this, but this non-reproducibility in such a key area is deeply disturbing. Okay, other types of data. Well, I thought I'd mention this one since Oklahoma is a center for environmental and weather data. We have at my new laboratory, Rutherford Laboratory just outside Oxford, a center for environmental data analysis, and they have a lot of data sets there. But the interesting thing is that you need a lot of computing, but you also need to get the data. And moving lots of data around is a very complicated thing. So they have built a very interesting architecture which brings compute and data completely together. So it isn't like a traditional supercomputer. It has a lot of computing power, but it also has the data very closely connected. You can get the data very quickly and you can do the calculations. And this is called Jasmine, and it's an interesting architecture which I think we'll see more of, and that's something I think, for example, you could do here. Then I looked in more detail at astronomy. I'll just pick out one of their problems. They do a lot with their telescopes. They have a very good archival system for the data for telescopes. And they have actually services that they offer on top of that, which are really quite impressive. They have links to the publications. They can link it to the data, telescopes and so on. But their problem is, if you look at the sustainability of data links in the papers, so you look at the data links that in the papers that were published in 2001, you look at them 10 years later, over 40% of the links no longer work. And that's a real issue, and we need to actually conquer that. Things like DOIs, digital object identifiers, are important. So those are just some of the issues looking at bioinformatics, environment, and this is astronomy. What we set up in 2004, recognizing some of the problems, I don't think we recognized all of them, but we set up a thing called the Digital Curation Center. And nowadays, you're obliged, if you do an NSF proposal or any agency's proposal, to have a data management plan. These people were looking at how you might do data management plans. So this was an attempt to bring together computer scientists with librarians, with different communities of scientists to work out what was needed to maintain the data for digital preservation, digital curation, what tools you needed to do it. So that's been going now 10 years. And it was funded by an organization which is not like the NSF, but it's a sort of It's rather like the Mellon Foundation, if you like. It's called JISC, and it's now offers universities a data archiving capability. They have shared data centers where universities, instead of keeping it on their own campus, they can put all their compute and their data in these shared data centers. So that's one of the things that they're doing. JISC also support our local, our UK-wide academic research network, and that's one of the things. But as you heard from the previous talks, it's expensive and difficult to curate data, and somebody actually will need to pay for it in the end. And I'm slightly concerned that we're worrying now about keeping too much data. I learned about data curation from one of my environmental friends who ran the British Atmospheric Data Centre, and his concern was creating what he called a worn archive, write once, read never. So he believed in order to avoid that, you really needed the scientists who took the data to be involved in deciding which data you keep long-term, which you can reproduce, which you can throw away. And these are the people. And it'll differ from community to community. I don't think you can have one size fits all. So in the UK, the research councils, which are, if you like, the divisions of NSF in the US, have decided what they're going to do about data. And this is one that's currently exercising a lot of university provosts and deans and so on. This is the Engineering and Physical Sciences Research Councils. This is what they expect. And research organizations, like universities, will ensure that EPSRC-funded research data is securely preserved for a minimum of 10 years from the date that any researcher privileged access period expires. So when you get your grant, you do your research, you're generating the data, you have privileged access for it, say, for 5 years. But after that, then the university is responsible for keeping that data for those 10 years. And then you can understand why people are really concerned about what's the cost of this, what's the data life cycle, who does the curation, and all these things. So that's one of the things that being grappled with in the UK. It's also something that's really concerning people here. There are repositories in the UK which are actually national ones. I told you the environmental data, but it doesn't include all the data. Some of the data will have to be held locally, and the same will be true in the US. That will be major NASA NOAA data centers, but there will also be ones in each university. You will need to keep some of the data, and I think, or have links to if it's stored nationally. So those are issues. Another issue is that if you want to move data around, you have a big data facility and you want to get it to researchers in Oklahoma, then it goes very fast over the backbone, but then it gets to the firewall of the university, goes through the university firewall, and the packets of data get all mixed up with email, with web searching, with videos, the teaching, and so on. And to avoid that, and so instead it goes very fast till it gets to the firewall, and then goes incredibly slowly, this huge amounts of data to where the researcher needs to be. And so this is an architecture called a Science DMZ, which actually enables you to identify that this is data coming from this facility and it needs to go somewhere particular on campus, and it catches it before the firewall and diverts it. And this has now been implemented by the NSF in something like over 100 universities, and I suspect Oklahoma University is one of them. But you might want to think about something like that if you're really going to have a collaboratory between the 3 universities in Oklahoma. Maybe you need something like this for routing data between the universities to where the compute sites are, where the researchers are, where the facilities are. It's something that I think needs to be thought about. So let me just conclude. I was giving a talk at the International Data Curation Conference last year. It was 10 years since they set up the Digital Curation Center. And I asked a few of the scientist friends what had happened in the last 10 years. And this is Jim Frew at the University of California, Santa Barbara. I asked him, had there been progress in 10 years? And this is what he said. The biggest change is the fact that now they're obliged to have a data management plan. That came from the OSTP memo that you saw. So now NSF insists you have a data management plan, and that had made scientists at least pretend to take data curation seriously. They at least have to say what they're going to do, even if they don't do it. I asked him whether there are better curated databases, more of them. He said, yes, there are, but the percentage may not be increasing because there are many more databases. So yes, there are more good curated databases, but not necessarily an increasing percentage. And then he had two interesting things which I think is relevant to this discussion. One was what he called Frew's first law: scientists don't write metadata. Right? That's typically not in what they normally do. The second law is any scientist can be forced to write bad metadata. And so his view was that you need systems, that will automate the capture. When you take the data, will automate the generation of metadata as much as possible. And those systems can be built, and some of them exist and partially exist and so on. That's something we can really work on together. But we also have people who do know about metadata. They're called librarians, science librarians, subject librarians. And actually, what he believes and what I believe is that really a role for the research library is assisting the researchers in actually archiving in the institutional repository their research paper linked to their actual data that's relevant to that. And that's really, I think, the major role for research libraries, to put yourself right at the front, and so you can have the paper, you can go to the data, you can add your data, you can write another paper, and it can really speed up the whole of the scientific research process. And it really starts, I think, with institutional repositories and the university research libraries. I care about libraries, but libraries need to change to take on this and to work with scientists to understand, not only scientists, because as James will undoubtedly tell me afterwards, I forgot to mention digital humanities. It's increasingly more digital. You have mixtures of digital and physical and so on. It's a complicated business, but digital is going to be there, and you need to use the expertise of the librarians, and they need to work with scientists and researchers of all types to understand that. Because otherwise, you know, why do you have a lovely building? Everybody loves libraries, but actually if students don't go in them, what's the point? One of my friends is the librarian at the Chinese Academy of Sciences Library, and he has a library in Beijing, and it's a gigantic building. And his problem is that nobody goes there anymore. So what do? Do you just have empty racks of journals with nobody actually goes and touches them? You have to actually invent the library, make it. It needs to be essential to the process of research, to actually really be assisting researchers doing their research. And I think that's the challenge for libraries. And I think it's a good one. And I think Rick and I have been working with how Department of Energy could do something good. And I think Oklahoma can really have a role there. And by putting your three universities together, you can really make something that people know what research you've done. They cite your research. It really is reputation management. Putting Oklahoma high up the list of places you want to know if they're doing research on weather, if they're doing research on climate, animal-borne human diseases, or whatever it is, you need to know that. So I think that's all I'm going to say at the moment, but thank you very much for listening.
Hi, everyone. I'm Kenneth Sewell. I'm Vice President for Research at Oklahoma State University. And as we move into this more interactive, reactive part of our program today, I want to welcome some guests that we have with us that I will only briefly introduce them so as to preserve time for reaction and interaction. So first of all, I'm just going in the order they're on my page. I think they might even, no, they're not quite sitting in that order. Chris Fennell is a theoretical computational chemist who works with me over in Stillwater at Oklahoma State University, will be joining us. Rose Gamble, who's a computer science faculty member at the University of Tulsa, and sitting next to her is Samuel Husky, classics and letters. You mentioned digital humanities earlier, and he's here at University of Oklahoma. And then next there is Toney Hey, founding member of the founding board of the University of Washington iSchool. Really spans a great range of expertise, starting, I believe, in physics yourself, as Dr. McKeever, but certainly moving more into the role of the digital libraries and information science. So what I would like to suggest that we do for just a few moments, kind of coming down the line a bit, is for each of our guest panelists to just mention briefly how this topic interacts with his or her individual discipline and individual work. And then if you could, and this is dropping it on you kind of last minute, since we're going to start with Chris, you get the shortest notice on this. What you see as one of the bigger challenges associated with thinking about open data as it relates to your particular work. So just kind of a couple of minutes down the line before we go to questions that will be more interactive with the whole group. So.
All right. Well, thank you for having me here as part of this. So I'm a fairly new faculty member at Oklahoma State University, but this whole idea of open data, open access data is something that was a real concern for me starting off. And one of the things I really liked about what Toney Hey said was data curation is a big problem. And that's one of the issues, at least when you're in the field that I'm in, where, so like I do theoretical chemistry. So we develop models on computers and we generate lots and lots and lots and lots and lots of data. So we sort of have a different problem than an experimental colleague of mine that I might collaborate with, where they would basically go through and focus on making their one molecule and identifying a structure. They'll get a spectrum, then they have these chunks of data that they make, and then they're basically trying to interpret that data. Well, I'm sort of in the other end. So we generate lots of data, enormous amounts of data, and we have to try to tease information out of that data or tease meaning out of that data. And the whole idea of trying to communicate that data to other scientists is, like, I was sort of brought up on it in my group, or at least in my training, that we needed to try to think about, okay, making sure that our science was open so that someone else could actually go through and do or reproduce the work that we actually had. So how do you actually make it so that another scientist can reproduce your findings? That's something that every one of us, or I guess every one of the data generators basically has to think about and curate your own data set. So like when Toney Hey was saying that yes, we needed to, every discipline sort of has a different approach for data curation or different strategies and different problems with data curation. That's sort of one thing I sort of see all the time, at least in what I do. So like figuring out, I've had experiences where you come up with a system for yourself, and then you say, okay, well, I'm going to try to provide the most important data, the analyzed data, sort of at a certain level, and make that open access and available through supplementary materials and papers, and that's something I always try to do in there. And it's actually served myself pretty well in discussions with other colleagues where I'd have people come up to me and said, thank you for putting this data in your supplementary materials, because they ended up publishing a paper that used my data directly to actually enhance their technique. So having this available is critically important, and it's, it's a difficult problem making sure that this is all available, but it's something that, it's sort of core to at least the things that I do. So I guess maybe pass on.
Well, I think curating and capturing the metadata was a very important point. Some of the things that we do some human studies, and whenever you capture that kind of data, you sometimes put it in a form that you can understand it and you can analyze it, but you might not be thinking about how you have to formulate that data for somebody to reproduce your work. That's sort of one point. Another thing that NSF is doing that we were just recently funded at the University of Tulsa was to build a test bed. And the test bed is to do cybersecurity experimentation on heavy vehicles, so like semi-trucks and buses. And what NSF wants is that they not only want us to build this test bed, so we'll have some real truck parts and some simulations, but we need to provide remote access to a community who may want to experiment with that test bed. And so that means keeping the experimental data available, but then also allowing them to, well, essentially run attacks on the test bed and having to be able to reset it, and also then having to manage this community and how they then sign up to use the test bed. So the NSF appears to be looking at a lot more ways to sort of focus these kind of test beds at a university and then having them reach out to the community so these experiments can be done without everyone having to purchase their own heavy truck or bus, for example. So that's another thing that's going on at the University of Tulsa. And the third thing, though, about data they want to bring up is the issue of private data. So we are working with a lot of companies to look at the way their data is transmitted securely and to analyze it and to possibly do some predictive analytics. But that particular data is totally confidential. And even if we make it vanilla in some way to release it, it's going to be almost impossible to really pull everything out that it's not going to be identifiable. And of course, the companies don't want it. So there's an issue there where we want to be able to do the research, but we're not going to be able to release that data. So that's the way it's.
Okay.
What really struck me about what Toney Hey said just now was the laws that he mentioned on I think it was one of the last slides, Frew's first and second laws. The first one being that scientists don't write metadata. I think that definitely, or I know that definitely applies to humanities scholars too. Humanists don't write metadata, or at least they don't think they do. In fact, in general, scholars in the humanities, at least in classics where I do my work, they're very much tied to print publications. But what we're doing with the Digital Latin Library Project is to help them understand that the information on the page in front of them is data and can be freed from the printed page to do interesting things with. So I gave a presentation just last week, sort of an introduction to digital humanities, in which I showed a printed page, traditional representation of a critical edition of a Latin text, and then a digital version of that, which looked kind of like that. But then I showed them my colleagues' visualizations of that data, storyline visualizations, pixel-based visualizations, and the reaction in the room was, what's that? And how do I do anything with it? So once we started talking about that, though, they began to realize the potential for dealing with the information that has always been sort of trapped on the printed page in one representation of the data in a much more fluid format. But that means also, and to return to this law that humanists don't write metadata, it is a struggle to get scholars to feel comfortable with the notion of putting data out there, and what do you do with it? And one of the things we're struggling with is figuring out how to get how to facilitate the creation of this data so that authors who are used to working in in an environment where they're just word processing or typing or whatever. They're actually thinking deliberately about the information that they're producing and how it might be used in different ways. So there's a small core of people who are moving in that direction and trying to push the discipline ahead, but I think we encounter the same challenges that you mentioned in your talk that face the scientific community. How to ensure the long-term usage of that data and availability of the data. Another question that you touched on briefly that I'd like to hear more about is how to evaluate the creation and management of data as an act of scholarship, because that is very near and dear to the hearts of many of my colleagues.
Thank you. Jesse?
Well, I feel like my whole career has been starting with the world of the closed world, right out to trying to sell people the idea that they should have open scholarship and open data. I first started off at Caltech on a data compilation high energy physics. My memory is most of photocopying. I don't seem to think we got much further than that. I then went to work for CERN in Geneva, and one of the fundamental things we did was really simple, was collating papers at the end of the week to say, here are the new preprints, they were called, the preprints of the papers that people all over the world could then find out about the new papers and read them quickly. Very simple ideas, which is now done digitally, much more simply than we did then, but the ideas were there. I then went to IBM, who had this very internal world, as you were mentioning. We had huge resources, pioneers in computing and libraries, but most of it was IBM confidential, IBM internal use only. The one good thing we did was setting up a local community of libraries, trying to share information both with industry libraries, public libraries, university libraries. We did try to get wider communities, but it was a slow business. I then went to work for the University of Southampton, and we did some of the pioneering work with institutional repositories, really trying to understand how you get academic scholarship more easily out there, and also to be accountable, as he was saying. How do you within the university know what papers you produced? So we did some of the selling job of going out to different departments, say both to arts and science. And in the arts community, it was very hard, where people were saying, no, this is mine, I don't want people to know. I've done all this work with the British Library, but I want to get on and do it. I don't want to share it with other people. So we had to work on people to say, look, how do we show, you've done this work, you want to show other people what you've done. Right. So it was a selling job of saying, look at this wonderful stuff you've done. Don't be afraid to share it. So first of all, it was the papers, but in arts, it could be your paintings, it could be your books. It was a whole different collection of things. We then went on to look at how do we manage this repository, how do we link out the data? And we worked on a project called Cladier with the British Atmospheric Data Service, where we tried to say, how do we link their data into a repository? If you can want to go from the paper to the data, what do you do? And that was a very interesting time where big battles between librarians and data scientists and the scientists. And there were some crucial things that happened, and I think we've now learned a bit more, and we're getting there, but we haven't quite finished yet, was how to link the data into the papers. And at the end of it, with a lot of improvement of metadata and battles between who did it, who wrote it, but we had to break down the databases more clearly with the metadata in order to be able to link to the specific things. And I think we've got further probably in producing this now, but there's a lot more work to do to make it more open and more freely available. So I think that was a very positive thing we did. The other thing was to make sure that the data was representative. One of the things they went on to do afterwards was see if you could make a journal for the data so that the people who produced the data were recognized for what they'd done, and it wasn't just the papers that were important. So I enjoyed being part of that, but I feel that I'd like to see how much has happened in other areas that could follow on from that.
Fantastic. As Kelvin and myself and Marilyn and Janet Haggerty, our colleague at the University of Tulsa, were first planning today, it was very important for us to make time in our limited schedule for there to be interaction. And so that now is the time for those of you here on site as well as at Tulsa had the opportunity to communicate questions through Marilyn. If you have questions, please make those known now since we are streaming. It's very important that we get a microphone to you to ask that question. And then we've got the entire group of panelists here who could be a resource in answering that question. And please don't be shy, because if you don't talk, we'll talk amongst ourselves here till the cows come home. So.
Well, I'm happy to report that the University of Tulsa is participating in full force, and I have a question from them. This is from, I love this name, Maurizio Papa. So what do you think might be the impact of cybersecurity research in these three areas? 1, production or being the source of open data, perhaps sanitized, to help us develop and test new cybersecurity tools and solutions. 2, regulating access to the data. And 3, protection of sensitive information, either by having direct access to the data or by inferring sensitive info from open data.
Okay, I'll have a try. And then, yes, I mean, the problem of secure access to the data, if it's open and general to the general public, that's one thing, but not all data you'll want that, so you have to have levels of access, and I think that's something that computer science work can actually do. You also need to make sure that people don't break in and trash your data, so you do need to have secure backups, and there's a project in the library at Stanford, lots of copies, keep stuff safe, which is a well-known project. And then there may be parts of your repository which are, you know, secret, military secure or whatever, where you need different levels of security. So I see lots of potential applications for cybersecurity research with repositories, and actually it could be a very useful playground for trying out some of these techniques. So I think it's, I would be very interested to know more about what you're doing.
Other responses there? Other questions?
So you mentioned a journal, a concept of a journal basically for data, in addition to having regular publications with persistent data identifiers and so on. Does that exist now? Is there say, a journal, and I can envision in my own field, a journal of meteorological data where data could mean observational data, could mean results from simulation data sets and things like that. Is there such a thing where you'd have like a 2-page descriptor of the data set and then the data set access itself, and that itself would be a scholarly contribution? Does that exist today? I was very intrigued by what you said.
This one, this I think was a project which didn't, I'm not sure it went on to be a permanent journal or not, but it was much more of a proof of concept. But I'm sure there are other ones out there that do the same thing. This was just very early days of even trying to see what really worked, even though that's not so long ago.
So I'm on the board of a nature journal called Nature Data, which actually is not so much about storing data, but actually storing extra information about the methodologies and things like that. But I do believe there are some journals. I think CoData is sponsoring a journal of data. I don't know quite what their criteria are, because, you know, they can't take petabytes of data, so I don't actually know what exactly they do. I just would like to the audience, in case you're not aware, that you have a real firebrand for open access in your midst. The person who started it all, essentially, was actually the dean you have here was at Los Alamos, and Richard worked with Paul Ginsberg with the original archive, and so that all started open access started really making your papers available, started with arXiv, with Ginsberg and Reclus at Los Alamos, and Ginsberg actually influenced the National Library of Medicine, which is at PubMed Central. He influenced our colleague at Southampton, Stephen Harner, that did ePrints. So a lot of it came from the original work at arXiv. So I thought you should know his dark background.
We have another question from the University of Tulsa from Justin Fuller, who is proud to have us know he's a graduate of OU 2005. Dr. Hey mentioned funding in his talk. Housing and transmitting data has costs, as well as hiring those who write scientific software and curate the data. Is Dr. Hey aware of any figures for the typical cost for a university the size of the one Oklahoma research institution to make the transformation he describes?
I don't have figures at my fingertips. I gave the rather extreme example of Swissprot, which has 40 permanent curators on one database. But I think that's an extreme example. But the organization I mentioned, JISC, in the UK, has quite a lot of papers written about the costs of curating data, the costs of preserving data. And I would recommend studying some of those, and I can certainly leave some links, or if you email me, I can send some links to these papers. But certainly these things are a real cost. What worries me more than the costs, I'm afraid, I'm no longer dean, so I don't have to worry about it. But I do worry about scientific career. There are people who are very talented at writing scientific software, and they're very specialized. They have to use these very complicated supercomputers which have complicated hierarchies, processes, and all sorts of things. And really, the whole basis for simulation and modeling at the high end depends on such people. I mean, and I worry that they're not sufficiently valued, that they have a career path, they go from temporary position to temporary position. I think you need to do that. And I think, similarly, there needs to be something for data scientists. Now, data scientists is a very popular term. It's one of these industry hype terms like big data, data science and stuff. For me, it encompasses sort of three phases of what you would do. There's a sort of data engineer, that's the nitty-gritty to get the stuff off the measuring apparatus, the CCDs, the satellites or whatever, into a form that you can give to scientists, and the data analysts can go and then use all sorts of clever combinations of statistical methods, machine learning, Bayesian networks and stuff like this to analyze the data. And then there's a data curation piece, and they may not be in the same faculty, may not be in the same department, but there needs to be some sort of career path for people like that. Brian Lawrence, who used to run the British Atmospheric Data Centre, yes, used to very much be concerned about the career path for the people who look after data. And I'm afraid they do have a sort of second-class status in science, and much of science now depends on the existence of these well-curated databases. And you know, it would be nice if maybe there needs to be a data science undergraduate degree or data science masters or something like that, and also some people where people who with those skills for software engineering and for data science can actually live in a university and have some prospects for promotion. So I think that's a real challenge, and I don't have the answer for this.
The career path issue, I think, is very important there. I know that our university, like many others at Oklahoma State University, we have taken to hiring individuals like you're talking about centrally. I employ some in the vice president for research part of the university, and that brings those experts to bear, and is a great tool for many of the faculty on campus, and is an employment opportunity for those individuals. But it's not quite the same as the career path that a young faculty member comes in with prospects of promotion from assistant to associate to full and tenure. We haven't worked that out yet. It's a temporary stopgap. Kelvin's got one more, and then maybe I'll finish with one. And
Okay.
Yeah.
So Toney has written recently on reproducibility of research results.
in the context of computer code, which is a very, very important issue. So for all the folks up there, Sam, this is for you too. There is always a question. I say that in the sense that he doesn't do computer simulations, but he certainly uses code. But the question really does concern the issue of storing results versus recreating results if they're easily recreatable. So one could argue that if you have a text in Latin and in classics that's been around for 300 years, for example, or something like that, 200 years, the text has survived this long, but if you, based on some of what Tony was saying, you digitize that, suppose the text goes away, then 20 years from now you can't possibly read the digital thing. But the text would certainly still be there, right? So I guess the question ultimately I have is, when do you make the decision about saving the data or simply taking what you have, whether it's a simulation code, whether it's a printed text, and reproducing it? And which one is most stable and persistent and cost effective? So it's a question I hope for everyone up there, because I think it's important.
Well,
Does that make sense?
If I may jump in first, some of the work that my colleague Chris Weaver is doing with visualization of textual data involves being able to save settings to produce a specific visualization of data, and then allow a user to manipulate the data for his or her own purposes and then return to that saved state, which is a matter of saving instructions for reproducing that particular visualization. So it's a very important question even in digital humanities, because we're talking about several different kinds of information that have to be coordinated in order to give a certain result, which is exactly what you're talking about. So it's a problem even in the humanities.
Well, it's a fairly large problem, at least in the things that I do, at least for computation or science-based research. So usually, well, personally, the way that I take it is, okay, I generate a lot of numbers, and these make enormous files, but then really most of that data is pretty useless in general. So the things that are critically important there are, okay, maybe subsets of that data. If your data has taken an enormous amount of effort to produce, or like you maybe got a grant through Exceed, and then you have you have 1 million hours on some Exceed resources, to 1 million compute hours, and you use that to generate data or generate sets of data, then you just sort of figure out, okay, well, other people, okay, it's going to be very, very difficult for someone else to reproduce the breadth of that data, because that's 1 million hours. They're going to have to write their own grant and get access to these resources to do that. So figuring out ways to say, okay, I can partition this up and take chunks of it out, and then at some point you have a package that somebody can download. And one of the ways that I've sort of approached this in a project, that we actually did have 2 million hours on Titan at one point. And we used this to generate lots and lots and lots of interaction potentials between molecules. And this was an enormous effort to actually generate these values initially. Then we decided, okay, well, how do we actually provide this in a way that someone else can use? So the way that we ended up doing it is basically crafting a little website and writing a piece of code that's interactive, where you can actually take those sets of data, interpolate between them, and get new data out of the data that we created. So then, in a sense, somebody can take full advantage of the effort that we put forward on the computer, or we put a million compute hours toward a project. Then we have it in a way that some other researcher can come in and effectively use Titan without ever having to write a proposal. So this is sort of, you can come up with fun projects to actually try to present your data and make it a little bit more interesting and accessible. And then I have it sort of interactive. You can go give a talk, and then you can actually show in real time, oh, it takes 8 seconds to actually generate what took us millions of hours on the computer. But you can get to that level if you bring down the important bits from that data. So, but yeah, like figuring out what do you save. And usually, at least in the stuff that we do, like the initialization files, the little program that's made to actually craft that whole little molecular world, for instance, if you were trying to model something. So those things are critically important, and that's what I tell all my students to actually save. And when they generate these large files, like, okay, how long did it take you to make that? Do you really think we need to save that whole set of data? Can you just calculate the essential value that comes from that data and then have that in a file that you save? So you have sort of the initialization, you have the end output from a standard analysis procedure on there. And then if someone wanted to go back and reproduce, they could basically take these initial files if they really wanted to, if they did get this big resource for computers, and then they wanted to put the effort to actually totally reproduce that, then they could. But then figuring out a way to make it a little bit more accessible, I think that's sort of a fun thing to do. Yeah, you probably would get a different result in some times. So that's sort of the issue with sort of the simulation field. You have to come up with, okay, addressing a problem and figuring out what's important about the simulation. Are you sampling in the proper ensemble? And if you are sampling in the proper ensemble, it doesn't really matter what the fine detail is, because really the end result, the value from that particular simulation comes in how do you actually process that in the end. So then you'll have some error associated at the very end right there, exactly like a Monte Carlo type thing. Mm-hmm.
If I may, again, something that Chris mentioned just now really resonates with the work that we do on the Digital Latin Library project. When we're producing critical editions of a Latin text, that word critical is very important. It's a critical perspective on the information. There might be a giant pile of information behind it, but it's the critical perspective that is the thing that's published. And the encoding that goes into it is what reproduces that critical perspective that gives you a sense of the argument behind the publication.
Maybe ask one final wrap-up question. I know we're running out of time, and I certainly think we would probably all agree we could listen to any of these individuals for a long, long time, let alone the brief time we've had. So I really appreciate that. One of the things I've really appreciated about this entire session today is that it has been all about the possibilities and the ways that open data and open access to data can enhance our science and enhance even our individual careers as scientists and as scholars. But we also have this notion of a mandate through some of the actions, at least in the United States, but some in Europe as well. And as someone who deals a lot with compliance in my own world, I've also dealt with plenty of folks doing data management plans or even archiving their data in the aftermath of having presented a data management plan that I would characterize as compliance oriented and sort of minimally, how can I write a data management plan that will sort of pass muster and get this over with? How can I archive these data in a way that I can say I did what I said I would do, but not really seeing any possibility for this being an enhancement? So my question is the mandate helpful, or is the mandate getting in our way and making it more likely that we will have worn databases as opposed to focusing on the impact of data sharing and open data? Is the mandate helping or getting in the way?
I'm torn because I came from this is a great idea, this is what we should do, we will help you do it. So we help the scientists get their metadata better. We try to make it easier for them to do it so they'd want to do it. But then I've gradually seen all these mandates come in, and I'm very torn, but I think it's probably inevitable. But I'd like to see that the structure of how you do it is so it doesn't feel like a mandate, that you do it because you want to do it, and that there's a mandate. It doesn't matter whether there's a mandate there, it's there, but you're doing it anyway, and that's what's happening, and that's the real world, and I think that's the transition I've seen.
Well, for someone who's had to comply with that mandate for an NSF, I think it's given researchers at least the opportunity to understand how to share their data. So before the mandate, sure, you were supposed to disseminate and leave things public, but now when you have to write it down, you have to really consider, are you going to have it really open access? If you have computer programs along with the data, that, that which generated the data, do you open them up, or do you have a request system? And now even the NSF has started their own sort of websites, their own virtual organizations for various programs where they want you to disseminate the data. So I think the mandate has been helpful in that we now at least think about something that we hadn't before.
I think I need to agree with my wife.
Yes, you should. I will tell you that right now.
No, in this respect. Namely, that I think you really need to convince people of the worthwhileness. It isn't just something doing it for the sake of it. You really want people to understand the benefits. And there are two, I hear all the things about privacy and all this stuff, and medical data is particularly complicated. But there are two sites that are well worth looking. One is ADNI, A-D-N-I, for Alzheimer's patients, and the other one is ENDAR for autism. And they have lots of charities doing various studies, but typically with small samples. And these two groups, in the autism and the Alzheimer's, they've agreed to pool their data. And it's totally remarkable that they've actually pooled their data, and people can now write papers on data that they didn't take. And so I think having started in those two things, they see clear benefits for doing that. And so I do think that you need to get people doing it and seeing the value of it. But I would actually look to the experience of the NIH with PubMed Central. When it was voluntary, they got 20% compliance. When it was passed into law by George W. Bush that you had to put your papers there, they went up to 70%. And it was only when they said they'd delay your next grant, it's been going up 0.5% a month ever since. So to get the final bits, you're going to have some compliance. And the mandate seems to me, yes, you'd like them to understand that people always have other things to do. So you need to have a little bit of pressure.
Well, I think it's appropriate that Tony got the last word in this panel, and our final remarks, I believe, are coming from Steve McKeever.
My wife, my sister was a Latin teacher.
Well, thank you. Thank you all to the panelists, and especially to you, Tony, for your remarks. I've learned a lot here this afternoon, and I hope you have too. Certainly this area is one of growing importance, and I can see that in fact it's almost, and perhaps it really is, a whole new area of scholarship all by itself. It's got a lot of challenges, as I've heard, as we've all heard, some of which would include how and where to store the data, who pays for it, it is expensive, how to secure the data, who are the experts that look after the data and help the scientists access it, and what career paths should we, especially in academia, be thinking about for such experts. What is the format that should be used for the compilation of data? All of these things will also be discipline specific. And the persistence of the data, how long should we keep it for? And what data should we keep? What do we mean by data, by research data? I love the acronym WARN, write once, read never. Reminds me of some of my research papers. There's a whole myriad of questions and challenges here, but one thing about humankind never gives up on these challenges. Humans do, individuals do, but as a whole, we do not. And it's going to take folks like yourselves, I think, to lead us through this web of challenges to arrive at a situation whereby we don't look upon this as simply another mandate, another area of compliance that we have to deal with, but rather a vital component of our scholarly endeavors that we comply with because it's the right thing to do, just as much a vital component of our research as perhaps that instrument or that computer or that book. With that, I would like to once again thank all of our panelists and our guest speaker, Sir Toney Hey, and please join me in a round of applause in thanking all of them. And it was good that Toney did have the final word, which, as I recall, was always agree with your wife. Ladies and gentlemen, thank you very much.